Thank you all for coming back. We have joining us this morning, we're going to talk about microphones, and we have joining us Dr. Christian Hasselou. Chris is the founder of the MTSU Recording Industry Program. Guess who didn't mute their phone? I'm the one. And it says scam likely. I'm the one. He is the founder of the Recording Industry Program at MTSU that has become the Recording Industry Department of the Mass Studies, and he's Professor Emeritus there and has forgotten more than most of us know. So he's going to share what he remembers this morning about microphones, which is why we only gave him 30 minutes. Chris?
Thank you, Frank. Good morning, everybody. I appreciate you coming out and braving the zombie apocalypse. I was late getting here this morning. I had to go down to Lower Broad Street. Back in an alley, I met a guy who said he could provide me with hand sanitizer and toilet paper. Turned out to be a scam. It was just Cornhuskers lotion and old issues of the Tennessean, so I didn't. Frank asked me to open up this microphone things and share with you my 55 years worth of experience studying and teaching and using microphones. I said, sure, how much time did I have? And he said, 30 minutes. I said, oh, okay. But he did want to hit basics, and some of this may be pretty basic for some of you. I'll try to move it along and interject where I can my experience as it applies to live venue audio. I'm kind of a studio guy by trade, but I've done a little bit of the live stuff, and so I will use that. So let's see the PowerPoint here. There we go. Let me back up. Oop. I'm sorry. You've seen it all already. There we go. All right. This is a typical microphone specification sheet from our folks, friends at DPA. And there are 28 items and two big graphs that go along with this. And we could spend 15 or 20 minutes on each one of these 28 and not be spending too much time on that. We're not going to do that today. We're just going to hit the highlights. But this does tell you everything that you would need to know about the microphone except for one very, very important specification, and that is how much it costs, because budget is always a consideration. But we're going to hit just a few of the things today. This is what I'm going to try to get through in the 30 minutes here. Again, a review maybe for some of you, but hopefully I can add a little something to each of these things. So we're going to talk about the transducer type, talk about the pickup patterns, talk about the frequency response, and talk about the relationship between all of those things, because each one of those areas impacts the other, and all of them are going to impact how you're going to use your microphones. So let's run through the basic transducer types. There are about 7 or 8 ways that we can convert sound into voltage. Of those, only 3 are really readily used in professional audio. The first of these is the ribbon, which works on an electromagnetic principle, where we have a very, very thin conductive ribbon that's suspended in a magnetic field. That ribbon is the diaphragm. You move the diaphragm with the air pressure, that induces voltage in there through a transformer typically. Let me stand in front of the speaker here and we'll get some feedback. I would call your attention to that transformer. All ribbon microphones until relatively recently have a transformer in there, and the quality of that transformer has a big impact on the quality of the sound you're going to get out of a ribbon microphone. Now, I say recently because there has been developments where a couple of companies have replaced that transformer with a buffer amplifier, an active unit. So you actually have to provide phantom power to the ribbon microphone of this type, which was just something you would never even want to consider back in the old days, where providing phantom power to a ribbon microphone could have catastrophic results. Here are the general characteristics of your ribbon. It's going to cost you some money. Not rugged. Again, there's an exception to that. We do have one company out there that's building some fairly rugged ribbons, but generally not rugged. Not designed to take high SPL. Not designed to be handheld. It's going to be very subject to any kind of noise. Really no wireless applications that I'm aware of. Very limited wireless applications. It's going to be pretty large. Almost always bidirectional, although again there are some exceptions to that, but usually bidirectional by design. Has a pretty low output. You're going to need some real good gain on your preamps to get signal out of this, but it does have a relatively flat frequency response, very low noise. There's really nothing in there to make noise other than the resistance of your transformer, and a really fast transient response. That is, it's going to pick up all the subtleties of your sound. Now, for your application worship, this is something you're probably not generally going to run into or use unless your ministry includes recording maybe the choir in a nice acoustic environment, in which case a pair of ribbon mics can give you a really, really wonderful recording at a much lower price than you might pay for instance, a condenser capacitor style microphone. So ribbons, let's go to the next one. This is your workhorse, your dynamic moving coil microphone. And again, it works on the principle of electromagnetic induction. You have a coil of wire attached to a diaphragm suspended in a magnetic field. When that diaphragm moves, the coil moves, and you induce voltage in that coil of wire. The thing I would point out here is compared to the ribbon, that diaphragm and coil is a fairly massive piece of equipment. So it's going to take a lot more energy to get that coil moving, and once it gets moving, it's not going to want to stop. And what that translates to is a less good transient response. It's just not going to catch the subtleties that you're going to get from your ribbon or your condenser microphone. General characteristics of your dynamic moving coil microphone: relatively low cost, that's good news. Very rugged construction, that's good news. Can take very high SPL, that's good news. Works as a handheld. Does have limited wireless application. There are a few wireless dynamics. Relatively large size, various pickup patterns, so you've got some options there. Frequency response is generally colored though. You're not going to get your flat frequency response from your moving coil dynamic microphones. Low output, again, you're going to need a lot of gain from your preamplifier sections to make this work, but again, very, very low noise. And again, as I mentioned earlier, a much slower transient response than either the ribbon or the condenser capacitor. And then finally we get to our condenser capacitor microphone. Capacitor is the right word today. Condenser is something that Frank and I would use, being kind of old school. So you'll hear them both use today. Everybody's going to call it a capacitor microphone. Works on the principle of electrostatic. We're going to have a capacitor, 2 plates. Capacitor stores an electrical charge. In this case, 1 plate. The back plate will be fixed. The front plate will be movable. That's the diaphragm. As sound pressure hits that plate, we're going to see a change in distance between the 2 plates. That change in distance is going to change the charge. So we're going to have a situation where the charge is going to go up, the charge is going to go down, and that varying charge translates into voltage, which becomes our audio signal. Now, let's talk about the general characteristics of our capacitor condenser microphone. Well, cost range is incredible. I mean, you can get them for incredibly low cost, not very good, or incredibly high. $8,000 would not be unheard of for a very high-end capacitor condenser microphone, so it can be very expensive. Can work very well as a handheld if that's what it's designed for. Some of our capacitor condenser microphones would never work as a handheld, but there are some designed to be that. Excellent wire application, wireless, as we'll hear in just a minute. Size ranges from very, very small, like those that are in my hearing aids here, all the way up to very, very large. Various pickup patterns, and it may be switchable pickup pattern. Here's the bad news: it does require a power source. So we've got basically three options on our power source. You have your batteries. Batteries are great. You know what the best thing that batteries do? They run out of power right in the middle of your show. So, but they're portable. That's a good thing. Or you can have an external power supply. It's kind of a problem. Something else to hook up and carry around. Or, of course, you can use the phantom power, the 48 volts that's provided in pretty much all consoles. That runs right down your mic line. Frequency response can be incredibly flat, incredibly transparent. You do get a really high output. That's really good. You can keep those preamp levels down. But you're also going to get some noise because it's going to have an active element. So all condenser capacitor microphones are going to have a preamp built into them. And that is going to require that power source. And it's going to generate noise. Finally, we have very fast transient response. That diaphragm is really very, very low mass. It's right up there with that ribbon. It's going to be easy to move and easy to stop, and so you're going to get great subtle transient response out of these microphones. And let's see, finally, also typically, often, will include a pad and a low cut or high pass filter. All of the specialty mics today are of this condenser capacitor type. So pretty much anything that's out of the ordinary is going to be this type. Your Tie-Tac, your lavalier, headset, goosenecks, boundary, shotgun, stereo mics are virtually all condenser capacitor type today. Pickup polar pattern. Let me stop for just a moment since we're going to switch gears here and talk about the pattern. Anybody want to weigh in? Any questions on these types? You're like my classes at school. It's just like, it's early morning, and the early morning classes are great. The students are all half asleep. Is it any problems? Well, I'm running out of my 30 minutes, so I'm going to zoom along. Pickup pattern, polar pattern. Pickup pattern is the way the mic responds to sound coming from different directions. And one of the things you want to keep in mind, it is a three-dimensional pattern. A 3D, height, width, depth. And we're going to represent that as a polar pattern, which is our 2D representation of that actual 3D pattern. Very, very important. The pattern will change or may change with frequency. So quite often in the literature, you'll see a single drawing and say, well, that's a nice looking pattern. I can point it here and I'll pick up that mic. But they don't tell you, some of the manufacturers, that that pattern only exists at one very specific frequency, typically 1K, but not often. Sometimes they'll choose the frequency that gives them the best looking pattern. So you want to know that the pattern is going to look different at different frequencies. The other thing we want to know about patterns is that certain patterns, because of the way they're created, will create proximity effects. Proximity effects, a low frequency increase when the microphone is used very close to the sound source. And we'll take a look at those right here. So here we have an illustration of our off-axis coloration. And you can see our frequency response graph over here. There we go, look at that. So we have three graphs, one at 0 degrees, front of the mic, one at 90 degrees, the side of the mic, and one at 180 degrees, the back of the mic. And you can see those patterns are very, very different. Now, yes, that 180 degrees is considerably lower in level than the one at the front, but it's not nothing. As we'll demonstrate here in just a second, there is some sound getting into the back of that microphone, and that sound, unfortunately, is not very good. It's highly, highly colored, and you can see on this particular mic, it emphasizes those higher frequencies. Now, on the other graph here, we see our polar chart, and you can see that it looks like it might be several different microphones, but in fact, it's just one microphone whose pattern changes considerably with frequency. You can see at 20K, I have a very narrow pattern, so our high frequency is going to be very selective. But when we get down here to 500 hertz, it's practically an omni or all-directional microphone, and that needs to be kept in mind when we do our placement and selection. Proximity effect. Here we see a graph showing you the proximity effect. The microphone placed at 2 feet, 2 inches, 1 inch, and an 1/8 inch. And you can see there's almost a 15 dB increase at 200 hertz on this particular microphone. Now this could be a good thing if you're trying to emphasize low frequencies. Maybe you're putting that mic on a kick drum or a floor tom, something like that. But it can be a bad thing if you're not wanting to do that. If you've got a vocalist who's bringing that mic right up to their chin and lips, and all of a sudden they sound a lot like me, and that's to say too low. There's our polar graph. Keep in mind that 0 degrees is the front of the microphone. Be careful when you look at these graphs, because some of the manufacturers do not follow this 0 degrees at the top. Sometimes they turn that graph 90 degrees, so kind of make sure you know what you're looking at. And each one of those divisions is typically 5 dB loss of sensitivity as you go from out to in. Again, you have to be careful, look at the graph. Some of them use 10 dB, which kind of distorts the graph a little bit. And we'll remember that a 10 dB loss is approximately half the sound, or a 10 dB gain is approximately twice as loud. That's kind of a rule of thumb, so keep that. So we'll look at these different basic pickup patterns versus omnidirectional. Implies sounds coming from everywhere. Omnidirectionals are typically not a perfect sphere. There's always going to be a little bobble on the bottom of the, because of this case itself kind of gets in the way of that sound coming directly from the back. The thing about Omni is they have almost no off-axis coloration. That's good news. And no proximity effect. More good news. Excellent low frequency response. So if you're looking for something to get the low frequencies, you want to look at an Omni. It was let me break here in a little story. Some years ago, there was a group of naturalists in Africa studying the African elephants, and they had a sound recordist with them, and he was trying to mic these elephants. And the question is, what kind of a mic do you choose to mic an elephant? That's the question. And he happened to have an Omni in his kit, which he had set out just to kind of capture some, ambience while they were trying to get these elephants' noises. And he kept hearing this low frequency rumble. And he said, well, I was checking his equipment, what's this? And it turned out that this rumble was actually coming from the elephants. It was in that 50-20 subsonic area, and that the elephants were using this very low frequency to communicate miles and miles. And no one had ever been aware of it because it was below most human perception, but that omnidirectional microphone picked it up. So if anybody ever asks you, what mic do you use to mic an elephant? The answer is an Omni. Bad news, feedback. You're going to get sound from all directions, and if some of that sound's coming from your loudspeakers, you may have a problem with feedback. How do we create an Omni? Well, we put the diaphragm in a closed case. Don't let sound get in the back of the microphone. Any change on the front of the microphone is going to be reflected on the diaphragm. This is why we call them pressure microphones, because any pressure change on that diaphragm is going to cause that diaphragm to move, and we're going to get audio out of it. You notice in my diagram here, I do have one tiny little opening in the back of the microphone. We have to have an opening in there to equalize the air pressure so that the microphone diaphragm doesn't pop when we go over the top of the mountains. Our bidirectional or figure 8 pickup pattern, very common with our ribbon microphones. This is called a pressure gradient as opposed to a pressure microphone. Pressure gradient is the rate of change of pressure, and that's what this microphone is measuring. Sometimes called a velocity microphone. That's actually incorrect, but that term is often still applied, even though it's not right. Figure 8 pattern. The nice thing about the bidirectional pickup pattern is the dead sides are really dead. And if you look at this here, boy, at 270 and 90, there's really nothing getting in there, and we'll demonstrate that here in just a second. Remember that the front and back lobes are out of polarity with each other, which actually you can use in our mid-side style miking. And you are going to get some off-axis coloration, not a lot in most cases, but you will get good proximity effect off of your figure 8 pattern. And this is how we're going to create our figure 8 pattern. We're going to have the mic open on the front and the back, like a ribbon microphone naturally is. Any sound coming directly from the sides will have equal pressure on both sides of your diaphragm. Diaphragm won't move. No audio. Our unidirectional, this is what we all use most of the time. Cardioid pattern. This is a pressure gradient style microphone. Lots and lots of off-axis coloration, even though our microphone designers have gotten really good at reducing this, there's still a lot of it. And we're going to get a good dose of proximity effect off of any unidirectional microphone as well. How do we create this? We put ports in the microphone. The ports allow the sound coming from the back to sneak into the back of the diaphragm, and we're going to get a equal and opposite pressure on either side of the diaphragm, and so the diaphragm is not going to move. If we stop here and kind of think about this for a while and say, how long does this path have to be? Excuse me. How long does this path have to be so that the other sound coming around the front arrives at the same time? And the answer is that depends on the frequency. So that means we have to have really multiple ports, but then there's kind of a limit to how many ports we can put in there. So eventually what happens is there are some frequencies that are not going to get canceled, which is why we're going to get this off-axis coloration. The other thing that is important is that in most moving coil dynamic microphones that have these ports, and condenser microphones that have these ports, the ports are nearly or totally invisible to the user because they're inside the windscreen or they're covered up with some kind of a shielding. Some of them are obvious, but most of the time you really can't tell that you're looking at something with opening in it. And if that opening becomes covered by gaffer's tape, when you tape that mic down, or if it gets covered up by a vocalist holding the mic and choking up on the mic, because typically their ports are at the top of the mic, not always though, all of a sudden that unidirectional microphone becomes a great omnidirectional microphone because you have closed the ports off, keeping that in mind. Lots of variation on the unidirectional microphone. We have the subcardioid, we have the supercardioid, and I would point out that lobe on the back of the supercardioid here. That lobe is hearing sound, and then we have our hypercardioid. That lobe gets even bigger. The front collapses a little bit, but we still have a pretty good sized lobe there. And our ultracardioid or shotgun mic, that typically used in film, video, and that kind of thing. With the size of the lobes on that, the mic folks in the film, video industry that carry these mics have to be very conscious of where those lobes are pointing and what kind of sound might be getting in the side and the back of these microphones. Switchable patterns, of course some mics have switchable pattern. Two ways to do a switchable pattern. In most cases, in our condenser capacitor microphones, you're going to have two diaphragms, a dual diaphragm. The two diaphragms will be back to back. Each of the diaphragms is a unidirectional diaphragm. And then within the microphone you have a matrix, which is a fancy name for a mixer, which is going to combine the output of these two diaphragms in various ways to create all of the pickup patterns that we just went over. Kind of interesting on this, I was taught, and you will still see in the literature, that if you, for instance, create an omnidirectional pickup pattern by combining the two unidirectional capsules in a dual diaphragm microphone, that you will still be subject to the limitations of that unidirectional pickup. That is, you are going to get a lot of proximity effect and you're going to get a lot of X-axis coloration. But recent research by Neumann has indicated that this is in fact not true, and that if you create an omni pattern with the two unidirectional microphones, you're still going to have an omni pattern without the problems. So that's just, I don't know, maybe a controversy, not really a controversy, but it's a place that needs some more research, that's for sure. The other way you can change a pickup pattern, and you'll see this in some smaller diaphragm condensers, is a switch that switches between uni and omni, and what they're doing is just simply closing the ports. So you close the ports, you got an omni, you open the ports, you have a unidirectional. And there have been a number of modern mics that switch between these two and are much simpler to operate and much simpler construction than you get with the multi-switchable systems. And then finally we get to frequency response. We want to remember that the frequency response is going to change as you change the sound axis, get off axis from the front, and you're going to change the frequency response when you get closer to the sound source with the proximity effect. In the frequency response written area, you will typically get from 50 hertz to 50 kilohertz, something like this. And quite often the manufacturers will not give you a dB range. It'll just say 50 hertz to 10K. Well, that's not really telling you too much. And quite often they'll call this the range, quote unquote. Now 50 hertz might be 20 dB down and 10K might be 20 dB down. So that written notification is not going to tell you a lot. What you really want to do is look at the graph, because the graph is really going to tell you what that frequency response is. The modern condenser capacitor microphones have incredibly flat, or can have incredibly flat frequency responses, whereas our moving coil microphones are almost always going to be somewhat colored. Now that's not necessarily a bad thing, but we need to be aware of it. Here are two frequency responses I pulled off the web here. Look at that one on the top. Wow. That's incredible. So flat. That mic's transparent. Whatever goes into that mic comes back out. Yeah, it stops at 50 hertz, so maybe that really low stuff is not getting in there. If they didn't measure it, they probably aren't really picking it up. But seeing something like that from when I first learned about microphones, it blows my mind that they're able to get that kind of response. Down below we have a frequency response from one of the most popular microphones ever manufactured. Some of you may recognize that. Not great down there at the bottom end, 10 dB down at 50 hertz. And they got that little bobble up there, 3K, 4 or 5K. And some people say, well, that's no good. That's not flat anymore. Actually, that's pretty good. Because that area where that little high frequency bobble is, right here, right there, that's where an awful lot of consonants are. And so rather than making things bad, it's actually going to help you out when you're doing dialogue or vocal. It's going to help the intelligibility factor by making sure those consonants are emphasized. I don't know if I'm getting down to the end here. I've been 30 minutes or not, but I do have a couple of final thoughts. Microphones are an incredibly precision measurement devices. We use 1 Pascal as a reference for some microphone measurements. 1 Pascal is something like 0.001 pounds per square inch. I mean, the pressure that we're talking about is just minuscule, minuscule pressure. And you want to treat it like you were having a finely tuned instrument, and even the cheap ones. And so just dumping it in the door, or not covering it up, or leaving it on the stand all the time, or it's going to be subjected to changes in temperature and whatever else is going on in the environment. Not a good idea. I try to get my students to really treat the microphones with great respect and care. And sometimes I'm successful, sometimes I'm not, but I try to do that. When choosing microphones, I always, being a studio guy, I don't care what they look like. I don't care what they sound like. But if you are in live entertainment, particularly if you're doing video, you've got to give some thought to the visual aesthetics of the microphone. And then let's see, point of potential failure, PPF, for live sound, as well as in the studio. I like to hit my students with this idea that where is it going to fail? It's going to happen eventually. And try to know where it's going to fail, where it might fail. Try to mitigate that, or if you can't mitigate it, be ready. And so I always, for instance, you're going to hear about, for instance, wireless in just a minute. Well, wireless is a tremendous thing to be able to get the freedom to go wherever the artist or the speaker wishes to go and not be trailing along a mic cable. But you know what? That mic cable's never going to fail. Where all those other things, every place that you go through, you got a place where it might fail. So I always have my students think about that. Let me end with a little thought experiment, if you would. Help me out with this, or do it in your own mind. Let's think about the listener experience in your audience. And let's assign that experience 100%. Not 100% good, 100% bad. Whatever it's good, audio or bad, or just whatever it is, it's 100%. And then let's go through the audio chain. Microphone, preamp, wireless system, converters, console, processors, speaker system, crossover amp, box, speakers, out to the listener. And let's assign to each one of these elements some part of that 100%. Everybody doing that in their mind there? How much for the speaker? How much for the crossover? How much for the power amp? How much for the mixer? How much for the wireless system or the preamp? And then how much for the microphone? Everybody kind of, boy, don't you love those consoles? I walked through the demo area this morning, and every time I walk by one of those consoles, I just, wow, look at that. So cool. And they're so cool, and they're so powerful today. And then speakers, same thing. Speakers are fantastic the way they can make these speakers today. So efficient. So good sounding. But then the question is, all that stuff after the microphone, you can really wreck your sound. But you can really never make it better than it comes out of that microphone. I got a couple of nods there. So that's where it really starts. And if you've got the right microphone for the right application, with the right placement, all the rest of that stuff is just going to be gravy. I'm saying 50% on that microphone and placement. Placement's important. And the rest of that stuff important. Oh, you got to use it. But that's why I dwell so much in my classes about the microphone. Couple of pieces of information here. There are some fantastic websites out there where you can find this information and much, much more. The Mike University by DPA, the Bosch Communications, and the Shure Audio Institute. There's also a great website called Microphone-Data, and it's you have to register, but it's completely free, no ads. So it's a non-profit, and you can find every spec sheet for every microphone ever made, almost. There's just thousands and thousands of microphones listed on that. So I would recommend those. A couple of books. The very famous microphone handbook by John Ergel, no longer in print, but available on eBay and also on Amazon. And then down at the bottom, the sound recording handbook by John Warham, also out of print, but available on eBay and Amazon. All the fundamentals, a little bit of math, and then the Ergel book has been reproduced and kind of modernized by the AES, and I believe, Frank, that's still available through the AES. Questions?
Yeah. Anybody have any questions for Chris? Questions on microphones?
Check, check. Couple of demos.
Very quickly here, we're going to go through.
Check, check.
Nothing inside.
Yeah, nothing there. Be great. And let me just do one little. So this is our hypercardioid. And this is also our hypercardioid. Don't forget, the back of that mic is really live, and if that's a podium, you got a problem. Okay?
If that lobe is pointing towards a monitor, you've got a problem.
That's it.
You angle that sucker like that, and that lobe is, that's a recipe. That's another recipe for problems.
So I hit 30 minutes, is that right?
Yeah.
I hit 30 minutes. Jason,
Yep.
are you ready?
I am.
Thank you all.
Thank you, Chris.